Today we're going to be talking about the concept of source transformation. And maximum power transfer. All right, so the first thing that I want to introduce you all to is the concept of a practical source. Okay. So we're going to start with a practical voltage source over here on the left. And to form a practical voltage source, we have an ideal voltage source with some source voltage Vs connected in series to some resistance Rs, like so. So this is a practical voltage source, or what we're going to consider a practical voltage source, because it does a better job of modeling real voltage sources like batteries and things like that than an ideal source does. So what is the biggest difference between an ideal source and a practical source? Well, an ideal source, voltage source, can have any amount of current leaving its positive polarity terminal, including an infinite amount of current. Whereas a real battery or something like that obviously cannot. What limits the amount of current that can be output by a real battery is the internal resistance of the battery cell itself, which we are modeling as this resistor Rs in series. So as Rs gets smaller and smaller and smaller, or approaches 0 ohms, our practical voltage source looks more and more like an ideal voltage source. So when we are designing a voltage source for like an electronics application, like one of those voltage sources that we have around the room that you guys have used in your experiments, we want to design that such that the internal resistance of the source is as small as possible. Now, for the ones that we have in this room, they're very, very cheap and very, very crappy, as I'm sure you guys have noticed. So they don't actually have a particularly good internal source resistance. It's on the order of a few ohms, where typically speaking, for most well-designed DC power supplies and things like that, it's on the order of tens of milliohms or smaller. Okay. Now, on the flip side of things, we have a practical current source, which contains an ideal current source Is connected in parallel with some resistance Rs, like so. Okay. So for an ideal current source, it could effectively have an infinitely large voltage drop across its terminals if it were connected to nothing, which we know physically is impossible. We can't generate an infinite amount of voltage because that would mean we were transferring an infinite amount of energy, and that would violate one of the laws of thermodynamics, all that kind of good stuff. So the source resistance Rs here effectively winds up limiting the amount of voltage that we can ever see across the terminals of this practical voltage source. So this is how we model current sources that are made from transistors, usually in the upper level electrical engineering classes, as just an ideal current source in parallel with the resistance of the source. Okay. So let me write this down here. Practical current source So what we are going to figure out today is how we can transform between these two representations. So let me talk a little bit about what I mean by that. If we had some load resistance RL connected across the terminals of either of these sources, that load resistance would have some voltage drop over it and some current flowing through it. Is that somebody's phone or is that an actual alarm thing? Phone? Okay, so we don't need to, okay, good deal. All right, just making sure we don't need to get the hell out of here. All right, so if we connected a load resistance across the terminals of either this practical voltage source or this practical current source, we would be able to measure a voltage drop across that load resistance and a current flowing through that load resistance. Would the load resistance itself be able to tell whether it was connected to a voltage source or a current source? Absolutely not. So from the perspective of that load, it doesn't really care whether it's being supplied power from a practical voltage source or a practical current source. And from a circuit analysis perspective, we don't really care either. We just want to use whichever representation makes our analysis easier. So being able to transform between those two different practical source representations can aid in our circuit analysis. So it's just another little tool in our toolbox to try to make things easier on ourselves. Okay. So in order for us to switch between these two forms, we need to make sure that they are electrically equivalent to each other. Okay. So we have briefly touched on the concept of electrical equivalence a couple of times in this class, but I don't know that I've explicitly used those words. So let's talk about what it means, okay? So electrical equivalence two circuits or networks, etc., are electrically equivalent when the new circuit retains all of the electrical characteristics of the original network or circuit. Let's call it a circuit since we used circuit before. So for example, let's say that I have a simple system where I have a voltage source connected to a network of resistors. Let's make this real easy. Let's call it resistor R1 in series with resistor R2. Okay. Let's define this voltage here, VL, as our load voltage. In this case, our load voltage VL is exactly equal to our source voltage VS, right? Let's define this current flowing through our load as IL, and using Ohm's law, we could say that IL would be equal to VS divided by R1 plus R2. And the power absorbed by our load would be VL times IL, which is just going to look like VS squared divided by R1 plus R2. Over here on the right-hand side, we're going to have our voltage source VS connected to a single resistor whose value R will be equal to R1 plus R2. The voltage drop across our load is still VS. The current flowing through our load is still VS over R, which would be same as VS over R1 plus R2. And then the power absorbed by our load would be VL times IL, which is going to look like VS squared divided by R1 plus R2. So we can say that this network here, containing these two resistors in series, is electrically equivalent to this network over here, containing a single resistance whose value is the sum of those two resistors. And we could do this for parallel, or we could do it for literally any combination of resistors that we can determine the equivalent resistance of. We could also do it for sources, right? When we learned about combining voltage sources in series and combining current sources in parallel, we were doing the exact same thing. We were ensuring that we had two electrically equivalent networks before and after the combination of elements, okay? So this isn't new, we're just formally contextualizing things here, okay? So now, let's do the same treatment with our practical sources and see if we can tease out what conditions need to be met for them to be electrically equivalent. So over here on the left, I'm going to have a practical voltage source. So my voltage source is in series with some resistance RS. And then over here, I'm going to connect some arbitrary load resistance R sub L, like so. I'm going to define the voltage drop over my load positive polarity on top, and I'm going to define my current flowing into the load, like so. So what should my voltage VL be here? How can I figure that out? I'm mildly upset that nobody has answered this question yet. I mean, it could be that. It's not what I was expecting. So let me give you a hint as to what I'm expecting then. I have a voltage source connected to two resistors in series, and I want the voltage drop over one resistor. Exactly right. Voltage division, to me, would be the easiest way to determine this because I already have all of the information. I don't need to do any extra work whatsoever, right? So VL would be VS times RL over RS plus RL. What would my load current be for this circuit? Exactly right. So just using Ohm's law, we would have VS divided by RS plus RL. And multiplying these results together, I can find my power, right? So that's just going to look like Vs squared times RL over RS plus RL quantity squared. Did I multiply those two things together correctly? I think so as well. So these are our relationships for our practical voltage source connected to an arbitrary load resistance. Okay. Now, let's look at a practical current source connected to an arbitrary load resistance. Once again, I'm going to define my voltage drop across my load, positive polarity terminal on top, current entering my load like so. So how would I find my load voltage VL for this circuit? Any thoughts? Do I hear current division? So I would definitely use current division to find the current IL. So let's do that first. So that would look like IS times 1 over RL divided by 1 over RS plus 1 over RL. And I'm giving myself some space here because it's going to be hard for me to figure out from my IL relationships what conditions make these things equal. So I'm going to play around with this a little bit. So what I mean by that specifically is I'm going to multiply this 1 over RS by a factor of RL over RL. And I'm going to multiply this 1 over RL by a factor of RS over RS. And so what that's going to give me is IS. So I'm going to have 1 over RL divided by RS plus RL divided by RS times RL. When I divide by a fraction, that's the same thing as multiplying by the reciprocal, right? So I'm going to call that RS times RL over RS plus RL. So that's my denominator flipped over. And then I'm going to multiply that by 1 over RL. And we should see that this guy cancels this guy. And we're left with, sorry, I'm running out of room, IS times RS over RS plus RL. All right, so exactly right. So what Christina just suggested is that since that RS and RL are in parallel, the voltage VL will just be that current times that parallel resistance, which would look like IS times RS RL over RS plus RL. And we could have also gotten that result by taking our current for IL and multiplying it by RL. Okay. Lastly, down here, our power is just going to be the product of VL and IL. So we're going to have IS squared times RS squared times RL divided by RS plus RL quantity squared. So when I look at the voltage relationship or the current relationship or the power relationship, there is one single thing that needs to be true in order to make everything, every equation we have over here on the right equal to every equation we have over here on the left, thereby guaranteeing that the two circuits are electrically equivalent to each other. What is that thing? So let's look at the voltage relationship here, right? What do they have in common? So there is a factor of RL divided by RS plus RL that's common to both. So in order for these two things to be equal to each other, we would need VS to be equal to IS times RS. If we look at our current representation, we have a factor of 1 over RS plus RL in both representations, which means these things will be equal if VS is equal to IS times RS. What about the power relationship? We have a common factor of RL over RS plus RL squared. So once again, we'll see that our power will be equivalent on both sides of the equation if VS is equal to IS times RS. So this is how we convert between a practical voltage source and a practical current source. So let's say that I have an 8-volt source and a 5 ohm resistor. And I want to convert that circuit into a practical current source representation. My resistor value has to stay the same. So if I had a 5 ohm resistance, I have to continue having a 5 ohm resistance. What should the magnitude of this current source be? Eight over 5, right? Voltage divided by current. The relationship right here, by the way, is nothing more than Ohm's law, so it shouldn't be particularly difficult to remember because you've been using it for weeks at this point, right? So if we're trying to figure out what IS is, it'll be VS divided by RS. So this would look like 8/5 of an amp. One thing that I want to point out here when we're doing this transformation is that the head of our current arrow has to be associated with the positive polarity terminal of our voltage source, meaning that if we have positive polarity on top, the current's flowing up. If we have positive polarity terminal on right, the current will flow to the right. Positive polarity terminal is on bottom, the current will flow down. Positive polarity terminal is on the left, the current will flow to the left, okay? And vice versa. If the arrow is pointing up, the positive polarity terminal will be on top. If the arrow is pointing to the right, the positive polarity terminal will be on the right, et cetera, et cetera, et cetera. So that's how we transform between these things. So let's take a look at a big ugly circuit and use this particular transformation method to simplify the circuit down to something that we could actually solve. So let's say that I have a 5 amp source in parallel with a 3 ohm resistor like so. I'm going to put a 4 ohm resistor here. Seven ohm resistor here. Put a dependent current source 3Vx here. $17 ohm resistor here. Two ohm resistor across which our voltage Vx is defined. Nine ohm resistor. I'm going to scoot that over one square here. And a 1 amp source like so. So let me ask you guys a couple of questions about this particular circuit. How many nodes does it contain? 5. 4 on top and then the 1 on the bottom, right? How many meshes does it contain? 5. So 5 nodes and 5 meshes, okay? So if we had a computer handy, we could solve this circuit using nodal analysis or mesh analysis all day, every day, without too much difficulty. What if we don't have a computer handy? You cry, okay? That's fair. So within a few steps, we are actually going to be able to transform this circuit using source transformations into a single loop circuit that we could have analyzed on the third day of class. So let's identify some things. Do we have any practical voltage sources in this circuit? The answer is obviously no, because there are no voltage sources at all. How many practical current sources do I have? 3. Nothing stopping me from treating that dependent source in parallel with a resistor as a practical current source as well, right? So I have 3 different things that I can transform here, okay? Before we start on these transformations, and this is going to be another thing that'll be useful with this, is there any resistor combinations that I can make that would simplify this circuit? How? None of them are in parallel with each other, and none of them are in series with each other currently. So let's start things off here by doing a transformation for the practical current source to the left of this red dashed line, okay? And so what I like to do is I like to treat these as if I'm literally disconnecting this practical source, performing the transformation, and then reconnecting the practical source to the exact same terminals that I disconnected from, right? So I have a pair of terminals here and here that I'm going to disconnect everything to the left of, transform it, and then reconnect things. So what should the transformation of my 5 amp source in parallel with a 3 ohm resistor look like? It would indeed, because V is equal to I times R. So 5 amps times 3 ohms is 15 volts. And then I'm going to have my 3 ohm resistor connected in series. Once again, notice because my current was flowing up, my positive polarity terminal for my voltage source is on top. Okay. So I'm going to erase this practical current source and replace at the terminals with the electrically equivalent practical voltage source. So what did that transformation do? Did a couple of things, right? So our circuit went from having 5 meshes down to 4 meshes, which means we're a little closer to being able to apply mesh analysis to it if that was our method of choice here. It also placed the 3 ohm resistor in series with the 4 ohm resistor. So technically speaking, oh, and I need to draw the 15 here, my apologies there. Technically speaking, it introduced another node, but it's a node that we can immediately get rid of by doing a resistor combination, right? So what's 3 in series with 4 look like? 7, okay? So I'm going to erase my 4 ohm resistor there and just put a 7 ohm resistor here. Now, let's do another source transformation on that practical voltage source on the left, okay? So 15 volts in series with 7 ohms is going to look like what? So 15 over 7 amps. What should the direction of my current source be? Up, okay. What else? In parallel with 7 ohms, thank you. So once again, I'm going to erase this practical source entirely and replace it with an electrically equivalent network. Here we have 15 over 7 amps in parallel with 7 ohms. What I've done now is I have eliminated a node, but introduced another mesh. However, I can get rid of that new mesh by combining those 2 7 ohm resistors, which now appear in parallel, right? So 7 in parallel with 7 is 3.5, absolutely. So I am just going to call this 7 over 2 and erase this guy right here. Now, the last thing that I'm going to do is I'm going to do yet another source transformation on that leftmost practical source, okay? So 15 amps, there's going to be 15 sevenths of an amp in parallel with 7 halves of an ohm is going to look like what? "15 halves as my voltage magnitude," absolutely right. And what is that voltage source going to be connected to? In series or in parallel? In series, absolutely, thank you. So I'm going to come up here and replace things. So this is 7 halves of an ohm This is 15 halves of a volt. Okay. So I don't know that I can make the left-hand side of the circuit any more easy. Isaiah, what's up? Because that's the condition with which they'll be electrically equivalent to each other. So if we had the resistor in parallel with a voltage source, the voltage drop across the resistor would be fixed to be whatever the source resistance is, or excuse me, the source voltage is. And the current would also be fixed because it would just be whatever the source voltage is divided by the resistor value. So we're not doing any sort of transformation because everything is literally always a constant, right? So that's why it has to be the other way around. All right. Let's look at this practical current source on the right-hand side of the circuit, right? So I have a 1 amp source in parallel with a 9 ohm resistor. So what is this electrically equivalent to? A 9-volt source in series with a 9 ohm resistor. Absolutely right. So I can come up here and I can replace like so. Now, we do have a practical current source up here as well. And just for the sake of argument, we are going to do a transformation on it here in a moment. But before we do that, we could also observe that 7 halves ohm resistance is in series with the 9 volt, excuse me, with the 9 ohm resistance. My apologies, I wrote volts here. And similarly, we could see that the 15 halves volt source is in series with the 9 volt source. So we could do a resistor combination and a voltage source combination here to further simplify things, right? So what's 9 in series with 7.5 going to look like? 12.5. So 25 over 2. 18 plus 7 is 25. Yeah. So let's call this guy 25 halves of an ohm, which is going to get rid of this guy. And hopefully we all understand that these two voltage sources are of opposite polarities, so I need to subtract them. So what's 9 minus 15 halves? Three halves, yeah. So 1.5 or 3 halves, absolutely. All right. So the last thing that I want to do here is I'm going to transform my dependent, yes, Troy. Because they're in series. So let me redraw that portion really quickly here. So this was a 9 ohm resistor. And here was my 7/2 of an ohm resistor. So hopefully it should be fairly obvious that they have the same current flowing through them. If they have the same current flowing through them, they're in series. So it doesn't matter where they are. It doesn't matter on the left-hand side or the right-hand side. They just appear far away because of the way that I've drawn them. If I have two elements in series, does their order matter? No. So I could put the 9 ohm resistor down here and the 7/2 right here, and it would change nothing, and they would be touching each other, and then you would have agreed to it pretty much instantly, right? So anytime I have things carrying the same amount of current, so that the same current flows through all of the elements and does not have an opportunity to branch off, they're in series, regardless of whether they look like it or not. Good question. No, very, very good question. Yes. Give me just a second to redraw this, and then I need you to re-ask your question because I didn't quite understand it. If the 3.5 volt source were a current source, would those resistors have still been in series? Absolutely, because they would still have the exact same current flowing through them. All right. So I'm going to transform my dependent practical source here on top into a practical voltage source containing a dependent source. And so I'm going to do the exact same rules here. So my network looks something like this, where I have a 17 ohm resistor in parallel with a 3Vx current source. What should this transform into? This one's arguably a little bit harder, but only extraordinarily slightly. So what are the units on that 3 right there? So amps per volt, because this is a voltage controlled current source. So I have a factor of 3 amps per volt, and I'm going to multiply that by 17 ohms. Well, what's an ohm again? It's a volt per amp. So 3 amps per volt times 17 volts per amps gives me what? 51, just 3 times 17. So it should look like a 51 Vx voltage source. Will the positive polarity be terminal be on the left or the right? So it'll be on the right because the current was flowing to the right. Absolutely. So it corresponds with the head of the arrow. And that'll be in series with a 17 ohm resistor. So I can still do that transformation even though it contains a dependent source because the units will work out. So I'm going to disconnect this network. And replace it with a 51 Vx voltage source in series with a 17 ohm resistor. And as promised, we now have a single loop circuit that we could have analyzed on the 3rd day of class. We took an ugly, horrifying monster and used source transformations to get this into something significantly more manageable The process, I believe, wasn't particularly hard. Tedious, absolutely. We did a crap load of these transformations to make this work, but it did work. Now, this isn't the be-all, end-all way to do something like this, okay? It works. It's fairly simple to understand. What we're going to learn in our next class meeting is what's called Thevenin and Norton equivalent circuits. And this is another way to reduce a circuit down into a practical voltage source or practical current source representation. It is a bit more powerful because it can be applied to any two-terminal network, but it's significantly harder to understand kind of why it works in the process of it, okay? All right, so I believe, unless anybody has a question, which it looks like there may be one, yes. So you could, they are of opposite polarity, so you could call that 3/2 minus 51 Vx, but then you have this weird algebraic expression representing the voltage source, which nothing particularly wrong with that, but I would think that some of you guys might be a little confused by doing that. With their voltage sources in series, so they can absolutely be combined. I think there was a hand up in this area, maybe I just saw something at Alia. 3/2 is 9 minus 15/2. Right, so 9 is the same as 18/2. 18/2 minus 15/2 is 3/2. And they were subtracted the voltage sources because they were of opposite polarities. So if we imagine a current that was flowing around the loop, either in a clockwise direction or a counterclockwise direction, it would have hit the positive polarity terminal of one of the voltage sources first and the negative polarity terminal of the other voltage source, which means they have the opposite polarities. So they subtract. That's correct. Yes, ma'am. All right, any other questions about the source transformation side of this lecture? All right, so now we are going to take what we have learned and apply it to figure out what the maximum power transfer that a practical source can provide is. So this is going to involve a small amount of calculus. Just to give you guys a heads up. We're going to derive this explicitly for a practical voltage source, and then we can literally just source transform the results to figure out how it's going to work for a practical current source because they're electrically equivalent to each other. So let's say that we have a voltage source Vs in series with a resistance Rs, and this practical voltage source is used to supply power to some load resistance RL. Right? So we know that VL would just be Vs times RL over Rs plus RL using voltage division, exactly what we did earlier today, so nothing new here. We know that IL will be Vs divided by Rs plus RL, and we know that the power absorbed by our load will be Vs squared times RL over Rs plus RL squared. So if I were to plot the power absorbed by my load as a function of RL it would look something like this. Where way over here on the left-hand side, when our load resistance is exactly 0 ohms, we should expect to see 0 power absorbed, because if our load resistance is a short circuit, the voltage drop across it has to be 0, which means no power could be absorbed, right? On the other side of the spectrum, we have RL approaching infinity, where effectively our load is an open circuit, which means there's no current flowing through the resistance, which means it can't be absorbing power either, right? And then everything in between those endpoints of 0 and positive infinity is every possible resistor value we could ever think of, right? Well, there is exactly one resistor value at which maximum power transfer occurs. There we go. So we're going to take the derivative of our power relationship with respect to RL, set it equal to 0, and figure out what value of resistance RL causes maximum power transfer to occur. Okay. So the derivative of PL as a function of, RL with respect to RL is going to be the derivative with respect to RL of Vs squared times RL over Rs plus RL squared. So how do I take that derivative? So the quotient rule, right? So F prime G minus G prime of F over G squared, where F is the thing in the numerator or the function in the numerator, and G is the function in the denominator. Is that right? It's been a hot minute since I had to do this. Okay, so what's the derivative of the numerator with respect to RL? I hear whispering. Is this equation not the right way to do the quotient rule for taking a derivative? All right. So how do I take the derivative of the numerator with respect to RL? Just Vs squared, okay? Times Rs plus RL quantity squared, okay? Minus, so what's the derivative of the denominator? Times 1 because of the chain rule, right? Yeah. Times the numerator, which is going to look like Vs squared RL. And then all of this is going to be over Rs plus RL to the 4th power, right? And we want this thing to be equal to 0 in order to figure out what the maximum is, right? So we really only need to set the numerator to 0, because if the numerator is 0, the whole thing is 0, okay? So let's expand some things out here, okay? So I have Vs squared times, so let's see, Rs plus RL quantity squared is going to be Rs squared plus twice RL Rs plus RL squared minus twice Vs squared. Then I'm going to have Rs times RL plus RL squared. Is my algebra correct there? Did I get too fancy with my brackets? So I just took the 2Vs squared out and then distributed the RL on the very right side to the Rs plus RL bit. Okay. All right. This is equal to 0. So one thing that I know I can do off the bat is just divide both sides by Vs squared, because 0 divided by Vs squared is still going to look like 0. So that gets rid of some things. So that's going to leave me with Rs squared plus twice RL Rs plus RL squared minus twice Rs RL minus 2 RL squared is equal to 0. This guy cancels this guy, and I can add those two guys together. And so that's going to give me Rs squared is equal to RL squared. So from this, we can see that maximum power transfer occurs when our load resistance RL is exactly equal to our source resistance Rs. I'm going to write that down here. All right. So if we evaluate our power expression at RL is exactly equal to Rs, we can find that the maximum power that can be delivered by a practical voltage source, so that's going to be Vs squared times Rs divided by Rs plus Rs quantity squared. So that's going to look like Vs squared Rs over 4 Rs squared looks like 1/4 Vs squared divided by Rs. So this is the maximum power that can be delivered by a practical voltage source. What if we had an electrically equivalent practical current source? What's the relationship? Is would be equal to Vs divided by R. So all that's going to do is transform this to Is squared times Rs. So let's work one last example, and then I will stop ranting at you guys. This is the last topic that will be on your exam for Monday, by the way. So here's the circuit that we're going to look at. We have a 12-volt source, a 3-ohm resistor, a 6-ohm resistor, 7-ohm resistor, and then some arbitrary load resistance RL. And I want to know what value of RL will cause the remainder of the circuit to deliver the most power and what is the maximum power that can be absorbed by the resistance RL. So just as a heads up, this is pretty much exactly how I'm going to phrase your questions on your exam for this material as well. It's going to be a two-part thing where I give you a circuit like this. You have to effectively reduce everything that's connected to the load resistor down into either a practical voltage source representation or a practical current source representation. And then once you have that, whatever the resistance of the practical source is the answer to the first part, and then literally plug things into the equation to get the answer to the second part. So how do I make the circuit above look like this? Because that's how I solved the first part. So somebody tell me what to do. So a source transformation, absolutely. So what am I going to have, Troy? Okay, so 4 amps, is it going to be direction up or down? All right, so 4 amps up. What's going to happen to my 3 ohm resistor in parallel with the 4 amps? All right, what can I do now? Somebody else. All right, so what's 3 and 6 in parallel, Walker? Oh my God, you don't get a calculator for this. 2, absolutely. What can I do now? Okay, so what's that going to look like again? 8 volts in series with 2 ohms. Is the positive polarity going to be on top or bottom? What do I do now? Combine those 2 resistors. So 2 in series with 7 looks like 9 ohms. So what value of RL will cause the remainder of the circuit to deliver the most power? Nine ohms. What will the maximum power be? So it'll be 1/4 times 8 volts squared over 9 ohms is 64 over 36 watts. So let's see, that's divisible by 4, so that's 16 over 9. If my mental math is correct. All right, that's enough out of me. So let's talk about things like that really quickly. There are going to be problems that have multiple parts, essentially. Okay. And so what I mean by that specifically is, I might give you a problem that you have to analyze using nodal or mesh analysis, and I might ask for 2 or 3 different quantities. I'm going to try to limit it actually to 2 quantities per circuit so that you don't literally lose over a letter grade if you just cannot solve a single circuit kind of thing. For a problem like this, It is 2 parts, so I mean, that would be potentially be 9 points. So it's pretty important that you guys understand what it is you're trying to do. So I get asked a question a lot of what's the best way to study for one of these tests? And my answer invariably is go over your in-class assignments again. Go over the practice exams, which are just old tests from this class that I've uploaded to Moodle. They have been there since the first day of class. Doing the homework isn't a bad idea by any stretch of the imagination, but if you're looking specifically to review for the exams, I tell you guys to review the in-class assignments and the old tests because I wrote the in-class assignments and the old tests, and I'm writing the new test as well. So they should be similar in nature, scope, and all that kind of good stuff. Just as a heads up, the exam will have 25 questions, the first 5 of which are theory questions, which means it should be something about possibly those definitions that we talked about for the first few days. So, you know, what is voltage, what is current, what is power, what is energy? Could be a question like I might have a resistor, just labeled R, and then positive polarity terminal of the resistor labeled on one side, and then a current flowing into either the negative polarity terminal or the positive polarity terminal. And I might ask you how much power that resistor absorbs. And so the correct answer would be like V squared over R, I squared times R, and then depending on whether the current is flowing into the positive polarity terminal, it would be I times V. If the current were flowing into the negative polarity terminal, it would be negative I times V. That kind of thing. So reinforcing the passive sign convention and stuff like that. Might ask, a theory question might be like, what is the correct equations that relate power and energy or charge and current, things like that. Then we get into the circuit analysis questions. For the circuit analysis questions, you should expect to see the material on the exam in pretty much the exact same order that we covered it in class. So the first few things will be just basic relationships, and then as you get further into the exam, that's when you're expected to start applying nodal and mesh and stuff like that. And then it will wrap up with a problem extraordinarily similar to the one we just worked, because this is the last material on the exam. Some of the old tests are 35 questions long. This test, as I mentioned, is not going to be 35 questions long. It's only 25 questions to be completed in 2 hours because the dean got mad at me for making you guys take 3-hour tests that night. Yes.
Are some of the questions that you reduced from the 35 question test, like the big ugly circuit?
Gone.
Okay.
Yeah. So that actually begs another question. So the most difficult system of equations that I could ever expect you guys to be able to solve would be a 3-equation, 3 unknown system. I'm not saying that there isn't going to be things that look like a 4-equation, 4 unknown system. You will have to do either some sort of circuit simplification or a simple substitution type thing in order to get it from a 4x4 system to a 3x3 system. But I cannot give you anything beyond a 3x3 system because that's all your calculators can do. And it would be unfair to force everyone to buy that particular calculator until Casio starts sponsoring me as a teacher, and then everybody buy one of those. Yeah. Any other questions about the exam or anything? Yep, fair game. I'm not going to put that on the test. There might be a conceptual question about that, but I'm not going to make you do that particular calculation because we did it one time just to prove a point kind of thing. Yep. Yeah. If you look at the old tests and then you also look at my solutions to the old test, you will see, if you haven't already noticed, that I am a jerk. And I like to make exam questions particularly circuits that look really difficult, but if you know what you're doing, are incredibly trivial to solve for. So there will be circuits that look like they are begging for you to apply nodal or mesh analysis when you can actually just use Ohm's law to solve the damn thing in one step. So just, I talked about this, I think the other day, but I kind of go through a check down of, can I use Ohm's law? Can I use KCL? Can I use KVL? If I can't just solve it with a simple single equation, then I look for voltage division and current division. If I can't use those, I finally get to nodal analysis and mesh analysis. And that seems to be very different from the way that you guys tend to think, where you use nodal analysis to a lesser extent and mesh analysis to a much greater extent as a crutch to get you through this class. That will, I'm not going to lie, that will absolutely work for the most part for exam 1. For exam 2, it will work for parts of it. And for exam 3, you are just completely and utterly out of luck, because exam 3 contains material where we're going to be doing stuff with complex numbers, and your calculators literally cannot solve a system of equations that use complex numbers. So I'm trying to encourage you guys to understand and apply the fundamentals early, because that's what's going to get you through the last half of the class. Okay. Any other questions? You are free to bring colored pencils and all that kind of stuff. You are free to bring multiple calculators. I've definitely seen that, all that kind of stuff. You can't pass calculators around or anything like that. That would be considered cheating, which I have seen students try to do that. Absolutely not. But if you're a nerd like me and you like doing some of the math on a TI and some of the other types of math that we wind up doing on a Casio, then having one of each just makes sense. Nothing's going to require 2 calculators by any stretch of the imagination, but get plenty of sleep, do some deep breathing exercises, and realize that even if you bomb this test, if this is your worst exam score for the quarter, it only counts for half. So as long as you can pull above a 34 and you've been doing your homework, doing your labs, and doing your in-class assignments, an A is still mathematically possible.